Okay, welcome. As we move on to section 3.2, and we're going to define what it means to be a discrete probability distribution. Okay. So let's start off with the definition then. Let's just go ahead and start off with the definition. Okay, let's change this. Maybe let's try that. All right, so we'll say f of x is a probability mass function. F of x is a probability mass function. F of x is a probability mass function. We abbreviate that PMF. Probability mass function, or sometimes just a probability distribution. A probability distribution of the discrete random variable x, of the discrete random variable capital X, if for each x, for each little x, we have the following conditions. One, f of x is the probability that capital X takes on that value. 2, since this is a probability, these should all be non-negative. F of x is greater than or equal to 0 for each x. For each little x. And 3, the sum over all x added up all together. If these are all probabilities, we add all the probabilities, we should get to 1. We should get to 1, okay? All right. And then I'll throw in an asterisk here, if you will, really quick, just kind of at the end. Basically just saying that any value, little x, that is not explicitly assigned a positive probability is not explicitly assigned a positive probability. A positive probability is assumed to have probability 0. Assumed to have the probability that x takes on that value to be equal to 0. Okay. All right, so let's take a look at one of these things. So, for example, let's take the case where we toss 3 coins, right? We've looked at this before. So toss 3 coins. X, capital X, counts the number of heads. All right. Well, let's take a look at this. We already made a table in a previous video of the sample points, so let me just go through that real quickly. Shoot. So here are the cases. Heads, heads, or heads. That would be 3. Heads, heads, tails. That would be 2. And if you have this nearby in your notes, you could just kind of reference that. I just want this on the screen so that we can take a look at the probability mass function. Tails, heads, and heads. Tails, heads, and heads. Tails, heads, and tails is a 1. Tails, tails, and heads is a 1. And tails, all tails, there's a 0 heads there. Okay. All right. So in this case, think about this. These are all possible outcomes. Each outcome is equally likely, right? Each specific sample point, has probability of occurring Well, these are all possible outcomes. They're equally likely. There's 1, 2, 3, 4, 5, 6, 7, 8 of them. So each individual sample point has a probability 1/8 of occurring. Okay, so we can add those together then to determine what is the probability mass function of x. Probability mass function of capital X is this. For little x to take on the value 0, how many sample points take on the value 0? Just the one. So f of x then is 1/8. How about 1? Well, that would be equivalent to getting 1 head, and we see that there are 2 instances where we get 1 head. We take a look at these right here, right? And so that is 2/8. What about 2? Let's take a look at counting the 2's here. You've got, oh, what's happening? Oh no. Oh no, new technology. I don't understand. 2/8. How about this? What do we got here? For 2. 1, 2, 3 of them. Bingo. So that would be 3/8, right? 3/8. And then the 3 is just 1/8 as well. What's wrong here? This does not add up to 1. Something went wrong, right? 1/8 plus 2/8 plus 3/8 plus 1/8 is not 1. Ah, we missed a 1 right here. There are 1, 2, 3 of those. Okay, so this should actually be 3/8. Let's go ahead and correct that. 3/8. 3/8. There we go. That's better. Let's just erase all this. 3/8. That is the probability mass function, okay? So now, with that, that's really nice because it's like, what's the probability that x is equal to 2? Well, it's 3/8. That would be the equivalent of getting 2 heads, right? Discrete probability mass function, okay? So sometimes it's as simple as just listing out the sample points. In other instances, it can be a little bit more complicated. Let's take a look at this example. A shipment of 20 computers contains 3 defective. There's 20 computers in a shipment. 3 of them are defective. If a school makes a random purchase of 2, makes a random purchase of 2. School makes a random purchase of 2. Find the probability distribution for the number of defectives purchased. Find the probability distribution for the number of defectives purchased. Okay, here we go. Let's go ahead and do this. Okay. All right, so here's how I'll set this up. Let's go ahead and let capital X then be the random variable whose values are the possible number of defective computers purchased. X is the random variable whose values are the possible number of defective computers purchased. Okay. So counting the number of possible defective computers purchased. So X could be, if they purchase 2 computers, out of 20, they could have 0 defective, 1 defective, or 2 defective, because there's 3 out of the whole lot that they are defective, and they could get 2 of those 3, right? Also, then the probability that x takes on any of those values, p of x equals x, this is the probability of choosing x defectives in the sample, is the probability of choosing little x defectives in the sample. In the sample. Okay. In the sample. So I'm writing that out because we're going to come up with a general result here, and then we'll get the specific values as well so we can put it in a table. Okay. So here's what choosing x defectives in the sample. Remember, we're only getting essentially a sample of 2. If they're purchasing 2, it's essentially just a sample of 2. All right. So before we write out the general formula, let's do it for an individual case. All right. Let's take a look at the case where, let's say, what is the probability of getting 0 defectives? Okay. This is accounting. We're taking a sample of 2 out of 20 total. So there are 20, choose 2 possible ways of getting 2 computers from the 20. Now, our numerator has to be the event of counting, or has to count the event. How many ways can it occur to get 2? If x is 0, that means there are no defectives. All right. Well, how many of the 20 are not defective? If 3 of them are defective, that means there are 17 that are not defective, and we want 2 of those. 2 of those, okay? And then at the same time, we also want 0 defective. So it'd be 17 choose 2 over 20 choose 2. If I want to be complete, I can say there are 3 defective, and I'm going to choose 0 there. Note that 3 choose 0 is just equal to 1. And so that's not really necessary, but it'll help us with a pattern here in a moment, okay? So let's take a look. 17 choose 2 over 20 choose 2. We need to run those through a calculator. We should get 68 over 95. 68 over 95, okay? That's the probability there. What's the other cases? X equals 1. You could get 1 defective. 1 defective. All right. Well, you're still picking 2 laptops from 20, but now of the 7, so in think of this 2 stages. Stage 1, you get 1 defective or 1 non-defective from the 17 good ones. For each of those ways, you need to choose 1 defective from those 3. So the event in this case has 17 choose 1 times 3 choose 1. And we can run that through a calculator, and we should find that to be 51 over 190. And in the last case, probability that x is equal to 2, well, 20 choose 2 computers. Of the 17, we pick 0 that are bad, and then we choose 2 from the 3 that are bad. So 3 choose 2 there over 20 choose 2. We run that through a calculator. We should get 3 over 190. Okay, so we take all of these. Those are all the 3 values that we can get in this case with a sample of 2. And so we can write out then the probability mass as a table if we want to as well. The probability mass function of x is in tabular form. X can take on the value 0, 1, or 2. And the probability that it does that in each case we have is 68 over 95. We have 51 over 190. And we have 3 over 190. So we have that right there in tabular form. Okay. I'll mention in general, we can sort of take all of this and put it in like a general combination formula, right? Or we say the probability that x takes on the value little x is equal to 20 choose 2. 20 choose 2. And let's think about this. If you get x defectives, that would be 3 choose x. Okay. And then how many are not defective? How many would not be defective then? 17 choose something here. Well, these numbers have to add up to 2 in the bottom of the combinations on top, right? You're getting 2. And so we're taking away x of them are defective. The rest of them are non-defective. So that'd be 2 minus x. And that is another way we could write this out in a general sense. And this would be for x equaling 0, 1, or 2. We'd write it out maybe like that. This is only good for x being 0, 1, or 2, right? Because we don't want to have a combination like 3 choose 4 or something, right? We're also only taking a sample of 2, so we have to have those limits, all right? Now, the downside of writing it like this that we have in blue here is just that this is a nice condensed formula, and it allows you to compute these probabilities, but it does not really tell you what those are. The tabular form is nice because you actually get to see the likelihood right there for you, right? And so you've got that. Also mentioned that putting this in tabular form also allows us to get a graphical representation or a plot of the probability mass function. And so oftentimes what we'll do is we'll just throw the probabilities on the vertical axis, the possible x values on the horizontal. So x can be 0, 1, or 2. This should have an upper bound of 1 here. Let's go 0.2, 0.4, 0.6, and 0.8, roughly speaking. Just a rough sketch here. All right, 68 over 95 is, something like 0.7-ish. So that would be, not there. Shoot. That would be right about here. And then 51 over 190 is about 0.3 something. That would be right about there. And then 3 over 190 is essentially 0. So that would be right about here. Okay. And so we can plot our probability mass functions as well. Probability mass functions as well. Okay, so it looks like that. The plot in the discrete sense is just these points. We do not connect the dots, remember? Because any value where x is not explicitly stated is meant to be 0 probability. So we don't need a plot like what is the probability x takes on the value 1/2. That's 0. Everything else is 0. Okay? In fact, you could, if you want to, we tend not to do this, but you could put your open dots here to show that it's 0 everywhere else. And then it would continue on in that fashion. And that would be also correct. Okay, that would be also correct. All right. I'm just mentioning this plot now in the discrete sense. It's relatively uninteresting here. However, the next section, when we get to continuous stuff, plotting the probability distributions is actually very useful. Okay, so we're just kind of laying some groundwork there. All right. That's enough for now. We'll leave it there. If you have questions specifically on this last example, or anything actually so far in this video, please post those in the discussion threads below. Otherwise, we'll see you in the next segment where we'll talk about the cumulative distribution function, or the CDF. See you in the next video.